Hello again, chemistry students. We're going to go ahead and move on to our next topic on our discussion of solutions. We're going to be looking today at different ways to calculate concentration. And so concentration is going to be the math part of this chapter. And so there are a few different ways that we're going to express this. I want to go over some problems in class on how to do this. And so you will not have any homework for this particular section. Later on, I will give you guys a worksheet that will help you go through some of these types of calculations, but I did want to go through a couple of these together in order for this to make sense. And so we're going to look at a few things today. We're going to see how concentration can be described using different units. We'll see how they are determined, and then we'll also be talking about molarity. And so molarity is the most important of the ways that we calculate concentration. So we have a few terms that we'll define here in just a minute. All right. Our first way that we can look at concentration is by using what's called a mass percentage. And notice that we have the word percent. And so whenever you hear the word percent, the number 100 should hopefully pop into your head. And so if we were to look, for example, we have some part of the solution, let's call this A, for whatever it might be. The mass percent of A, we're going to take the mass of A in solution, we're going to divide that by the total mass of the solution, and again, we're going to have to multiply by 100 because, again, it involves a percent. And so this is one of the ways that we can express a concentration. I want to go ahead and do a problem that involves calculation of a mass percentage. And so hold on just a second. All right, I found a problem. I'm going to put it on the board. I'll read you the question, and then we'll go over how you would set this up. So hold on just 1 second. All right, so this is going to be a mass percentage problem. All right, mass percentage. So here is the question. What is the percent by mass of sodium hydrogen carbonate, which is also sometimes referred to as sodium bicarbonate. This is found in baking soda, in a solution containing 20.0 grams NaHCO3 dissolved in 600.0 mils water. All right, and so I'm also going to tell you, because you're dealing with water, we're going to assume that the density of water is 1 gram per mole. So what we can say is that 1 milliliter of water equals 1 gram of water. And so under normal atmospheric conditions, we can hold this to be true. So 1 milliliter of water is the same as 1 gram of water. All right, so notice again, in order to calculate mass percentage, so we're going to be looking for the percent of the NaHCO3. In order to calculate this, we're going to take the mass of the sodium bicarbonate on top, the total mass of the solution on the bottom, and then multiply by 100 to get the percent. All right, and so what we'll do, notice that we're given 20.0 grams of sodium bicarbonate. So that's what's going to be going on the top. All right. Remember, the bottom number is the total mass of solution. And so I want to tell you again, a solution is made up of a solute and a solvent. So the solute is what's dissolved, and the solvent is what does the dissolving. And so typically, especially when you're looking at biology, the solvent is typically water. So we know that the sodium bicarbonate is the solute, the water, as usual, is the solvent. And so we need to find the total mass of these two. So notice we're going to have 20.0 grams of the sodium bicarbonate. We're given 600 mils of water. Remember that 1 mil of water is the same thing as 1 gram of water. So if we have 600 mils of water, we can say that we also have 600 grams of water. So we're going to add 600.0 grams of water. And then because it's a percentage, we have to multiply that by 100. All right, and so what we're going to do, I'm going to go ahead and take out my calculator, and then we're going to go ahead and calculate the percentage of the sodium bicarbonate in this solution. And so I'm going to take 20 grams on top, 20.0, and divide it by 620.0 and multiply by 100. And so when I go ahead and do that, I end up getting something roughly 3.2%. So roughly 3.2%. Notice that the answer is being expressed as a percentage. The grams on top would cancel with the grams on bottom, and so because we're multiplying by 100, we know that this is a percentage. So the percentage of this sodium bicarbonate solution in water works out to be 3.2%. All right, let's now look at another example of how to calculate concentration. So we have another concept called mole fraction, and so just as the name suggests, it involves a mole on the top and moles on the bottom. And so again, because these are on the top and the bottom, the moles will cancel out, and so this will be a unitless number. And so to find the mole fraction here, we take the moles of the solute and divide by the moles of the solution. Remember again, the solution is made up of both a solute and a solvent. And so on the bottom here, we have moles of solute plus moles of solvent. And so that would give us then the total moles of the solution. And so let us go ahead then and do an example of this type of concentration problem. And so I'm going to go ahead and do this. All right. We're going to go ahead and we're going to do a mole fraction problem. All right, so hold on just a second while I go find the problem. All right, so found a problem. And so I'm going to go ahead and write it out, and then we'll set it up, and then we'll solve it. And so here's the question. What is the mole fraction of sodium hydroxide, NaOH, in an aqueous solution? So as soon as you see the word aqueous, think aquarium or aquatic, and you know that you have water. So again, we see here that water is the solvent in this solution. So We have NaOH as our solute. Aqueous solution means that our solvent is water. And so it contains 22.8% NaOH by mass. All right, and so what we need to do is we need to, first of all, remember that we're looking for the moles of the solute divided by the moles of the solution. So I'm going to go ahead and put that up here. So X of NaOH is going to be the moles of NaOH over mole NaOH plus mole water. All right, so remember, just like with mass percentage, we have the mole of what we're interested in on top, and then we have the mole of the sodium hydroxide plus the mole of the water on the bottom. So again, this would represent the total moles in this solution. Notice that we're given the NaOH as a percentage, and so a very good way to help us out here is to assume that we have 100 grams total. And so we have assume we have 100 grams. And so by doing that, this percentage becomes a grams. And so we have 22.8 grams of sodium hydroxide. And therefore, if we want to, we can figure out how much water we have. We have a total of 100 grams. 22.8 of that is water, or sodium hydroxide, sorry. And so we end up calculating that we have 77.2 grams of water. All right. Notice, however, these are both being expressed as grams, but we're needing to find moles. And so if you remember back in our stoichiometry chapter, in order to go from grams to moles, we need to know the molar masses of the respective compounds. So we have sodium hydroxide and we have good old water. And so if you look at your periodic table, you'll see that the molar mass of sodium is approximately 23 grams per mole. Oxygen is roughly 16 grams per mole. Hydrogen is 1 gram per mole. 23 plus 16 plus 1 is 40 grams per mole. And so we can use that as our conversion factor to go from grams of NaOH to moles of NaOH. So let's go ahead and we'll do that now. 22.8 grams of sodium hydroxide. We're going to put the mole on top so that the grams go on bottom. The units will cancel out. We're going to take 22.8 divided by 40, and that should tell us the moles of the sodium hydroxide in the solution. And so when I go ahead and do that, I end up getting 0.57 moles. So we have 0.57 mole of sodium hydroxide. All right. We need to do the same thing now with water. We need to know the molar mass of water. If you guys remember when we were doing the hydrates, we have 2 hydrogens, which are each 1 gram per mole. Oxygen is 16 grams per mole. 16 plus 2 is 18 grams per mole. So remember, the molar mass of water is 18 grams per mole. We have 77.2 grams of water. We're going to multiply that. Again, we're going to put the mole of water on top. The 18 grams of water goes on the bottom. To calculate the moles of water, we're going to take 77.2 grams and divide it by 18 grams. And so when I do that, I get something roughly about 4.3. So I'm going to say 4.3 mole of water. All right, we're almost done. Notice now we have both the sodium hydroxide and the water in terms of mole. We look at our equation up here. We have the moles of the sodium hydroxide on top, and then the combination of the moles on the bottom. So we'll basically use these two numbers, plug them into our equation, and therefore solve this question. We'll have 0.57 mole NaOH on the top, 0.57 mole NaOH plus 4.3 mole water on the bottom. So again, based upon these two calculations, we plug them into our equation. And so I'm going to go ahead and do that in my calculator. And so when I go ahead and do that, I end up getting a mole fraction of roughly 0.12. Notice again, because the moles on top cancel with the moles on bottom, it's a unitless number, and so we end up getting 0.12 for our mole fraction. And so that would be how we would do that. All right, let us now focus on another type of solution concentration. Also, I wanted to point out some applications, depending upon what you're looking for, you might need to know the mole fraction of the solvent. So this would be solvent at the top instead of solute. But then the bottom number here obviously would still be the same because you're just looking at the total solution. So depending upon what the problem is looking for, you might be needing the moles of solvent on the top. However, for our purposes, we'll typically have the moles of solute on the top. So just wanted to point that out. All right. This is probably the most important concentration that we deal with in chemistry, and it's one that chemists use all the time. This is known as molarity. And if you notice again, at the front part of the word, you're going to see the word mole, because the mole is very important when it comes to measuring amount of stuff in chemistry. We're going to use the abbreviation capital M to symbolize molarity. To calculate molarity, we're going to take the moles of the solute and divide it by the liters of solution. So the solute is on top and the solution is on the bottom. And so because volume is temperature dependent, molarity can change with temperature. And so what I want to go ahead and do, I want to do a molarity problem with you guys. And so hold on just a second. Okay, let me find a molarity problem. All right, so let's go through an example of how we would calculate molarity based upon a particular situation. Right. Here's the question. What is the molarity of an aqueous solution? So again, you should be thinking about water containing 40.0 grams of glucose. And so for those of you in biology class, we are going to go ahead and sing the formula for glucose. That would be C6H12O6. In 1.5 liter of solution. All right, so the question here, what is the molarity of an aqueous solution containing 40.0 grams of C6H12O6 glucose in 1.5 liters of solution? And so I'm going to go ahead and put, again, the formula for calculating molarity. So to find molarity, it's the mole, in this case, of C6H12O6 over the liter of solution. Notice that this calculation depends upon those two things. We don't have the moles of glucose. However, we can convert from mass to moles, again by knowing the molar mass of glucose, and then we're provided the liters of solution, and so we can just plug this number directly in here. So before we calculate molarity, we first have to calculate the moles of glucose. And so we have C6H12O6, and so we first find the molar mass of C6H12O6. Notice that the formula for glucose, we have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. So we turn to our periodic table. Remember that carbon is roughly 12 grams per mole, hydrogen is only 1 gram per mole, and oxygen is approximately 16 grams per mole. And so we're going to take 6 times 12 grams per mole plus 12 times 1 gram per mole plus 6 times 16 grams per mole. So this represents the carbon, this represents the hydrogen, and this represents the oxygen. And so we'll plug this in our calculator to calculate first the molar mass of the glucose. And so I'm going to go ahead and do that. And so when I push this in my calculator, I see that I end up with 180 grams per mole. All right, so I've calculated first the molar mass of glucose. I'm going to use this as a conversion factor to go from grams of glucose to moles of glucose. And so I have 40.0 grams of C6H12O6. I'm going to go ahead and I'm going to put the 180 grams on the bottom so that the units cancel out. And therefore the 1 mole goes on the top. All right, I'm going to take 40 divided by our 180, and I end up getting 0.2 repeating. So I'll say 0.22. We have 0.22 mole of C6H12O6. We now know the moles of our solute. We are given the liters of solution, and so we can now go ahead and calculate the molarity. The molarity is going to be 0.22 mole of C6H12O6 divided by 1.5 liter of solution. So again, we take the mole over the liter. Here's our mole. We're told that we have 1.5 liters of solution, so that goes here. And so to calculate this, we're going to take 0.22 divided by 1.5. And so I'm going to end up with something roughly 0.15 molar. And I'm going to use the capital M as the abbreviation. And so we first of all needed to calculate the molar mass of our solute, which in this case was glucose. We found that to be 180. We use this then to go from the mass of the glucose to the moles of the glucose, which turned out to be 0.22 mole. We're told that we have 1.5 liters of solution. 0.22 mole divided by 1.5 liter works out to be 0.15 molar, capital M, C6H12O6. And so again, this is the most common type of concentration that we deal with in chemistry. And so hopefully that makes sense. All right, we're going to go ahead then and look now at another concentration. But before we do that, I want to talk to you about probably one of the most important equations that any chemist will use. In the lab, we typically don't have millions of bottles of different solutions. What we typically do is we have what's referred to as a stock concentration, and from that stock concentration, we take just a little bit of the volume out, and then we can use that then to dilute solutions. And so dilution is the opposite of concentration. So basically, a dilute solution has less concentration than what you start with. Typically in the lab, you would use what's known as a volumetric flask. And so I do have one right here. I want to point out, if you look right here, you're going to see a line etched into the glass. And so what this means is that if you were to fill this vessel up right to this point, it's going to equal exactly 250 milliliters, which as again is going to be about 0.25 liters. All right, why I'm bringing this up, you can use the dilution equation to calculate the concentration of your dilute solution. All right, and so this is going to look very similar to Boyle's law from the last chapter. It is not. We're going to be looking at M1 times V1 equals M2 times V2, where the M is molarity and V is volume. And so again, you would be given a stock concentration, you know how much you have, and so you're looking for a new concentration, and so typically in these problems you're going to be looking for V2. So you're going to be looking to see how much of the stock concentration you'll need in order to make the dilute solution. I again want to point out this is the most useful equation in all of chemistry, even more so than Pivnert or any of the other equations we talked about in the last chapter. When I was a researcher up in Columbus, I used the dilution equation almost every single day. And yes, it is that important. So I want to go ahead and go over a problem that involves calculating dilution. All right. So we're going to go ahead and do a dilution problem. All right, so let me go ahead and find the problem. All right, let me go ahead and write out the question, and then I will give you guys what it is, and we'll go from there. What volume of 3 molar potassium iodide, not King's Island, that's different. This is potassium iodide. Stock solution is needed to make 0.3 liter of 1.25 molar Ki. All right, so here's the question. What volume of 3 molar potassium iodide stock solution is needed to make 0.3 liter of 1.25 molar Ki? So in this problem, remember again, the most useful equation of all chemistry, M1 V1 equals M2 V2. This is going to represent our stock concentration and volume, and then this will be our dilution. So this is our stock, and this will therefore be the dilution. All right, so on the left we have our stock concentration and volume. On the right we have our dilute, and so the dilute concentration and volume. It doesn't matter which is this because again it's equal, but just for making it easy on ourselves, we'll just keep this as the stock. So what we're looking for in this problem is V1. And so what I'm going to do, I'm going to make myself a little easier. I'm going to move the M1 to the other side by dividing both sides by M1. And so I can rewrite this as V1 equals M2 V2 over M1. So again, I'm looking for V1. I want to undo the multiplication, so I divide both sides by M1. And so I can rearrange this then to solve for V1. This represents our M1. This is our V2 and our M2. So I just go ahead and plug in what I know, and then I can solve for V1. So V1 equals 1.25 molar times 0.3 liter on top, and then I'm going to divide this by 3 molar on the bottom. And so notice that the molars, the molarity here is going to cancel, and so then you're just going to be left with liters, which again is a measurement of volume. So the units do in fact balance out. All right, so we're going to go ahead and take 1.25 times 0.3 and divide that by 3. And so when we go ahead and we do that, we're going to end up getting 0.125 liters. All right. So what this means, in order to make up this dilute solution, if we want to make up 0.3 liters of 1.25 molar of Ki, if we start with 3 molar, we need to take from the 3 molar 0.125 liters, and then we'll add water then to bring it up to the 0.3 liters, and therefore we'll have a concentration of 1.25 molar. And so that is an example of a dilution type problem. And again, this is probably the most useful equation in all of chemistry. All right. We have, I believe, one more thing to talk about, maybe two. For whatever reason in science, again, for example, when you have mitosis and meiosis, or something, the words sometimes sound alike, but they have different concepts. And so we also have the case here in solution chemistry. We have molarity, but we also have a way of measuring called molality. And so molality, as you can see, still involves moles, but notice that we're going to be using a lowercase m as a symbol for this. So molarity has a capital M, molality has a lowercase m. And so to calculate the molality, it's going to again be the moles of solute, but the bottom number this time is kilograms of solvent. So notice in this case, we do not have volume. In this case, we have a mass, and specifically kilograms. And instead of solution, we have just the solvent. So remember, the solvent is what dissolves the solute to make a solution. Because neither moles nor mass change with temperature, molality, unlike molarity, is not temperature dependent. And so in a couple sections, we will see how molality is useful in doing some specific calculations involving changes in both freezing point and melting point. And so I want to go ahead then and do an example of a molality problem with you. And so I'm going to go ahead and turn your attention again up to the board. So this is going to be a molality problem. All right. Let me go ahead and find a question, and we'll go over how to do it. All right. So here's the question, and I'll read it. I'll go over it again in just a second. What is the molality of a solution containing 10.0 grams of sodium sulfate, Na2SO4, dissolved in 1,000.0 grams H2O. All right, so here's the question for molality. What is the molality of a solution containing 10.0 grams sodium sulfate dissolved in 1,000.0 grams of water? So let me go ahead and write up again the molality equation. Molality is equal to the mole of solute over the kilogram of solvent. So again, you have to be careful with how you name this. So this is molality, not molarity. Please don't confuse them. I know they sound a lot alike, but they're very different. Mole of solute over kilogram of solvent. Notice right now, we don't have either of those, and so let us first focus on calculating the mole of solute for the sodium sulfate. And so again, we have to remember that we have to first calculate the molar mass of the sodium sulfate, and then we can use that conversion factor to figure out the moles of solute, and then we'll then focus on the kilogram of solvent. So let's first calculate molar mass of Na2SO4. Notice that for this compound, we have 2 sodium atoms, 1 sulfur atom, and 4 oxygen atoms. And so we turn our periodic table. We see that sodium is approximately 23 grams per mole, sulfur is approximately 32 grams per mole, and oxygen is roughly 16 grams per mole. And so we're going to take 2 times 23 grams per mole plus 32 grams per mole plus 4 times 16 grams per mole. All right, so this part here is for the sodium, this is our sulfur, and this is our oxygen. So let's go ahead and calculate then the molar mass of the sodium sulfate. 2 times 23 plus 32 plus 4 times 16, and we end up getting 142 grams per mole. All right, this again will serve as our conversion factor as we go from mass to moles. We're told that we have 10.0 grams of the sodium sulfate. For our conversion factor, we're going to put the 142 grams on the bottom so that the units cancel out, and therefore the 1 mole of sodium sulfate goes on the top. Units cancel out. To calculate the moles of the solute, we're going to take 10 and we're going to divide that by 142. And so when we do that, we end up getting roughly 0.07 mole of the sodium sulfate. All right, so we calculated now. We have 0.07 mole of our solute. We have that number. Now we need to calculate the kilogram of solvent. Notice, however, we have 1,000 grams of water. We remember from last semester that there's 1,000 grams in a kilogram. And so we'll put the 1,000 grams on the bottom. Notice that not only does the unit cancel out, but the 1,000 cancels out. So we actually have 1 kilogram of water. This is actually very awesome because, again, the kilogram of solvent, which is going to be 1, what we do then is we just take 0.07 divided by 1, and that will give us 0.07 molality. So to calculate the molality, we take 0.07 mole of Na2SO4. We divide it by 1 kilogram of water, and so we end up getting 0.07 molal. We use the lowercase m for molality. We use the lowercase m for molality, and this is going to be Na2SO4. All right, and so again, we first of all had to calculate the molar mass of the sodium sulfate. Here, we use this then to convert from mass to mole. We know that there's a kilogram is the same thing as 1,000 grams. Molality is moles of solute over kilogram of solvent. 0.07 divided by 1 is 0.07 molal of sodium sulfate. All right. And so with that, we're going to go ahead and end today's topic. And so again, there's no homework that you guys need to work on tonight. I will give you guys a couple worksheets that will help you practice specifically with both molarity and dilution calculations, but that'll be in a few days. And so I hope you guys learned something today, and I also hope that you all have a great rest of your day. And I will talk with you guys again soon.